Okay, good day. This is Dual Enrollment Pre-Calculus. I'm Mr. McCulley, and this is Lesson 37, Geometric Sequence and Series. Let's get right to it. Today we are going to be talking about the explicit and recursive definition for equations of a geometric sequence and series. We're going to find the sum of both finite geometric series and the sum of infinite geometric series if all of the conditions are met. So let's talk about some definitions. First, geometric sequences. Whereas arithmetic sequences have a common difference, geometric sequences have a common ratio. So each term is multiplied by a common ratio. So here's a quick example. 1, 3, 9, 27, 81. This is a geometric sequence because this sequence has a common ratio of 3. So let's talk about some equations and formulas that you're going to have to know. First, a sub n equals a sub 1 times r to the n minus 1, where a sub 1 is the first term and r is the common ratio. That is the explicit form of a geometric sequence. And then to find the partial sum of the first n terms in a finite geometric series, you're going to say s sub n is the first term, a sub 1, times the quantity 1 minus the common ratio to the nth power all over 1 minus the common ratio again. And so here's some quick examples. The finite geometric series 1, 2, or 1, 3, 5, 1, 3, 9, 27, 81, 243. That thing would be rewritten for us as a sub n equal to the first term a sub 1 times the common ratio, which we can clearly see is r. Oh my goodness. A sub n equals 1 times the common ratio, which we know to be 3, times n minus 1. And we would write that as our final answer. We wouldn't write 1 times anything. We would say 3 to the n minus 1, put a box around that, and be done. If we wanted to find the first term, 6 terms of that series, here's 1, 2, 3, 4, 5, 6. So we know that. So I'm going to go back up to here. I'm going to say s sub 6 is equal to the first term, which was 1, times 1 minus the common ratio, 3 to the n, which we said was 6, all over 1 minus 3. And so we'll just grab our graphing calculator to calculate that for us. We'll go alpha, hit our y equals to bring up our fraction. We don't need the 1 times, so we're just going to go 1 minus 3 raised to the 6th power. We'll close that parenthesis, and then here on the bottom, we'll go 1 minus 3. We will hit enter, and so 364 is that sum. All right. Well, now, what about this particular series? 243, 81. If we flip it backwards, the one that we just did, we flip it backwards and go 243, 81, 27, 9, 3, 1, 1/3, 1/9, and then this plus dot 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 means that this goes to infinity. Well, this thing actually has a sum, and the reason that it has a sum is that while this series here had a common ratio of 3. We multiplied by 3 each time. This infinite geometric series has a common ratio of 1/3. We go 243 times a third is 81. 81 times a third is 27. 27 times a third is 9. 9 times a third is 3. And 3 times a third is 1, and so forth and so on. So this thing actually has a sum, and this one has a sum s, and notice there's no n there. Why? Because we're summing up all of the terms, the infinite number of terms, and that's just a sub 1 times 1 minus r, or divided by 1 minus r, provided that r is less than 1, or the absolute value of r is less than 1. So you could have a negative r, so like negative 1/2 would also be a common ratio that would, for an infinite series, that would have a sum. So how do I calculate this sum? This is just going to be s equals the first term, 243, over 1 minus 1/3 in this case. So we've got 243 all over 1/3, or 1 minus 1/3 is going to be 3/3 minus 1/3. So this will be 2/3. And so I'm going to grab my graphing calculator again, 2, 4, 3 divided by, and then we'll just go parentheses 2/3 like that, hit enter, and we get 364.5. So this is 364.5, and that's that total sum. All right, so an example, find the first 5 terms of a geometric series that has a first term of 5 and a common ratio of 2. Well, if that's true, then a sub n is going to equal to 5 times 2 to the n minus 1, and we will use our graphing calculator to get that for us. So we'll go to our y equals, we'll clear that out. We'll go 5 times 2 raised to the x minus 1. We'll go to our window here. We'll start our table at 1 and go by ones, leave everything on auto, and we'll hit graph there. So 5, 10, 20, 40, 80 is what we're looking for. And so 5, 10, 20, 40, 80, and you know what? I shouldn't put that. 40, 80. This sequence goes on forever, so let's go dot, dot, dot like that. That'll work. All right, next example. It says, find the first 5 terms of a geometric sequence with the following recursive definition. So here's our recursive definition. The first term is 80, and then a sub k sub plus 1. So the term next to it will be the previous term times a half. And so if we wanted to do that, the first term we said was 80, and so I'm not going to do all of them, but a sub 2 would be a sub 1 times a half. And we already know that a sub 1 is 80, so we'll go 80 times a half, that's 40, so the next term would be 40. And then a sub 3 would be a sub 2 times a half, which would be 40 times, oops, let's do it right, which would be 40 times a half, which would be 20. And so I see the pattern now. The next one would be 10, and the next one after that would be 5, dot, 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 and we're done. All right, next one. Find the sum of this thing. So I look at this, and this equation right here, that is a geometric series. If I were to put those out and start plugging in all these values, this series would be 4 plus 12 plus let's see, times 3, we'd get 36 plus dot, dot, dot until we had 20 terms there. So since it's a geometric series, I can find that sum using the sum equation that we had earlier. This one right here, we know what the first term is, we know how many terms they want us to figure out, and we know the common ratio. So we can say S sub 20, and I know that it's 20 because it says there are 1 to 20 terms. And so that first term is 4, and then the common ratio is 3, and we're going to raise that to the 20th power all over 1 minus 3. We'll grab our graphing calculator, we'll quit out of this, and then we'll clear all this stuff, and so we'll go alpha y equals, hit that. And then the first term, just got to check to make sure, the first term was 4, and then it'll be 1 minus the common ratio, which we said to be 3 for 20 terms. And then we'll put a parenthesis around that, come down here, 1 minus the common ratio 3, hit enter for that value, and it, ooh, that's a big number. Wow, gets big fast, geometric progression. Let's see here. 6973, 6973, 6973. I don't think that's the right place to put comma, so I won't. 6973, 568800. So 568800. 568800. So comma there, comma there, comma there. 6,973,568,800 is that total. Okay, so our next example here, write the following geometric series in summation notation. So the opposite of the last question, we're going to write this one in summation notation. So let's get a sum out here. sum. Okay, let's see here. I equals, actually, I should use, I think I'm going to use n. N equals 1. I don't know how many terms there are. I'm going to have to figure out what the upper bound is, but the series is going to be fairly easy. We're just going to use that, the general form of a geometric sequence written explicitly. All we need is the first term and the common ratio. That's easy. First term is 2. 2 times 3 is 16. 6, do it right there, Macaulay. 2 times 3 is 6. 3 times 6 is 18. 18 times 3 is 54. So I'm assuming that my common ratio is going to be 3 to the n minus 1. And now all I got to figure out to be done is this upper bound. Well, this is the nth term. This is the last term in that series. And yeah, let's do that. So I got to figure out what the n is. So a sub, we're going to say, no, we're not going to do that. We're going to say that our nth term is 4374. That's the nth term. Our equation to calculate that is 2 times 3 to the n minus 1. So now we're solving for n. We're going to solve for this n. Now, what do we got to do first? Well, don't be that guy. Common mistake that I see a lot in past tests. I can see these kids that'll go 2 times 3 first, and then I'll say 6 to the n minus 1. That's not right because you're breaking the order of operation. You're doing multiplication before you take care of exponents. So we're going to divide by 2 first. And so I come over here, and so 4,374 divided by 2 is 2187. So I got 2187 there equals 3 to the n minus 1. So I got to go all the way back to the second unit we did on logarithms to remember how to do this. I'm going to say take the ln of both sides. So I've got the ln of 2187 equals the ln of 3 to the n minus 1, and then I'm going to apply the property. You got to remember log base a of x to the n is equal, you can bring the n down in front, n log base a of x. And so I'll have n equal, or ln of 2187 equals n minus 1, and this is a quantity now, times the ln of 3. And so we're dividing by the ln of 3. And so I've got ln 2187 over the ln of 3. That'll leave us n minus 1. So we're going to add 1 and flip the equation. And so I'll have n by itself, and then I'll have the ln of 2187 all over the ln of 3, and then we got to add 1 to that. So graphic calculator, alpha y equals gives me my fractions. I need the ln of what we had in that last one, so 2187 divided by the ln of 3, and then we need to add 1 to that. And we hit enter in there. So there are 8 terms in that. This ends up being 8. That means that's our upper bound. Put a box around that and we are finished. Okay. It says determine if the following infinite series have a sum. If so, find the sum. So I look at this thing, 30 and then 15 and then 15 over 2 and then 15 over 4. Well, gotta figure out what the common ratio is. So 30 times a half is 15. 15 times a half is 15 over 2. 15 over 2 times a half is 15 over 4. So this thing has a common ratio of a half. And so since the absolute value of r is less than 1, this series has a sum. And it's a fairly easy one. It's just s equals the first term over 1 minus r. We saw that in an earlier part of the video. And the first term was 30 over 1 minus the common ratio. And the common ratio, clearly a half. And so we get 30. 1 minus a half is just a half. 30 pies divided into halves gives me 60 parts. And so that's that sum. All right. Oops, there's a part B. So I look at this next one right here, and let's see here. Let's see, a quarter times 2 is a half. A half times 2 is 1. 1 times 2 is 2. 2 times 2 is 4. So this has a common ratio of 2. That's how I get each term. This series does not have a sum. It diverges because the absolute value of r is greater than 1. So we don't have to answer that one. All right. Next, example, a deposit of $125 is made into an account beginning of each month that pays 3.5% interest compounded monthly for 5 years. This thing is called an annuity. This is a way that most of you guys will be saving money. Up until now in Algebra 2, we talked about putting like $50,000 in an account that pays 6% for 30 years, and how much would you have after that? Well, that's kind of cool if you have $50,000 that you can put into an account, but most of us, we're going to be saving in bits and bits, like monthly bits, like $25 a month. And I suggest that you get into some sort of annuity or 401k. 401k is a little bit different, but this gives you a good idea of what you can do. And 3.5% interest is actually pretty good right now. So let's talk about how we're going to do that. It says write a geometric series that models this situation. Okay, so if I put $125 into account at the beginning of each month that pays 3.5% monthly interest compounded monthly, that thing would look like this. It would be $125 times 1 plus 0.35 over 12, because it's, oops, I almost made a mistake there. Remember, 3.5% would be 0.035 over 12, and at the end of the month, it would just be 1 month. And then, so the next month after that, this first $125 that you put into the account, it actually moves over and becomes 1 plus 0.03 over 5 divided by 12 to the 2, because it's been calculating interest now for 2 months. And this is the new $125 that you put into the account at the beginning of the second month. Now, the third month starts. You put in $125, and this 120 at the end of the month, this $125 that you put in at the beginning of the first month moves over and becomes 0.035 divided by 2, and it's been calculated for 3 months. The second $125 moves over and it's been calculating interest for 2 months, and then the newest $125 is calculated interest at 0.035% compounded monthly for 1 month, and this continues for 5 years. So instead of writing all of these out, we'll put dot, 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 and we'll say in 5 years, 5 years times 12 months, that's 60 months. So after 60 months, this first $125 keeps moving down every month until that $125 has 1 plus 0.035 to the 12th for 60 months, and all of them continue to move down. And this one now, this first term here, represents the last $125 that you put in at the beginning of the month, and it was calculated interest for 1 month. So now we have a geometric series that models the situation. So now they want us to write this series in summation notation. Okay, sum equals, let's do I this time. I equals 1. We know that there are 60 iterations of that thing. And so what is the first term? Well, the first term is this entire thing right here, because
The next one would just be the original term times this part right here. So this is going to look a little funky. It's going to be 125 times 1 plus 0.035 over 12. This is my a sub 1. And then this next term is multiplied by 1 plus 0.035 over 12 to the n minus 1. And so this part right here is my common ratio. All right. Or at least I guess let's make it look a little bit nicer and say that just this portion right here is my common ratio and then my n minus 1. And so the first term, when n is 1, you get a 0 here, so this entire value becomes just 1, and then that's the original one. And then when n is 2, you've got this to the first times this again, that'll give me a squared value there. All right, there's part B. How much would a person have saved and the value of the annuity at the end of 5 years? Okay, so we need to know how much they saved. Well, that's easy. If I keep adding 125 every month, then the amount saved would just be $125 times 60 months gives me 125 times 60 is $7,500. So $7,500. But we want the value of the annuity. So we want the value of this sum here. So S sub 60 is going to equal, well, the first term was 125 times 1 plus 0.035 over 12. That's the first term. And then and again, I'm using S sub n equals a sub 1 times 1 minus r to the n all over 1 minus r. That's the equation that I'm using. And so there's my a sub 1. And then the common ratio will be 1 minus, let's see here, it'll be 1 plus 0, let's do that right, 1 minus 1 plus 0.035 over 12 to the 60th power all over 1 minus r, which again is 1 plus 0.035 over 12. And I don't want to type these things in 3 times. So let's learn a new calculator trick here. All right, so I'm going to go 1 plus, and I'll go alpha fraction, and we'll go 0.035 divided by 12, and we'll calculate what that is. Okay, we'll go 12. And what I'm going to do is I'm going to store that in, oops, I don't want to do that. Let's quit back out. I want to store that in, not a second, alpha A. I'm going to store that in A. I'm going to store that value in A right there. So now, since I have a value for A, I know what A is. If I come back here and I go 1 plus 0.035 over 12, that's going to be my A. The cool thing is I can say that S sub 60 is now 125 times A times 1 minus A to the 60th power all over 1 minus A. And that makes entering that a lot easier. So let's do that. Alpha, give me my fraction, 125, and then alpha A, parenthesis, 1 minus alpha A raised to the 60th power, and then all over 1 minus alpha A, calculate that. So $8,207.13. 8207.13. 8207.13. and comma there. Oh, look at that. I missed that. Let's rewrite that because I got a comma in the wrong place. Why would I put it there? So it was $7,500. So by doing the annuity, you actually earn $1,200 in interest. That's not too bad for 5 years, even though they get 3%. And so let's follow that on. Let's actually make a calculation here for multiple years. If we did that for our entire working career, let's see how much we would have saved. Just I got a little extra time. If you don't want to do this as kind of an extra, you can skip on to the end. But let's say I wanted to do this for my entire working career. So let's clear this out and let's just put that equation in. Instead of 60 months, let's do it as a variable. So it would be, let's go second alpha. Let's put our fraction bar in there. Let's go 125. Oops, that's 152. 125, and then alpha A, parentheses, 1 minus alpha A, and this time we're going to raise to the x because that's what's going to change. We're going to do different units of months, and then 1 minus alpha A again, and so then the next one, let's do 125 times x, and what that'll do is that'll calculate how much money we've actually saved over that time. And then let's change our table setup and let's go to ask like that. All right. And so let's go to our table. And if we go, so 60 months was 5 years, and that was how much we saved. So we saved $7,500 and we have $8,200 in the bank. So after 10 years, that would be $120 or 120 months. And after 120 months, we've saved $1,500 and we have in the bank $17,900, so almost $18,000. So we've almost made $3,000 already. And then after it will be 180, that would be 15 months or 15 years. And so after 15 years, we've saved $22,500, but we have $29,000 in the bank. That's a difference of almost 7,000. Actually, is $7,000. Then after 10 years, that would be $240 or 240 months. And after 240 months, we will have saved $3,000, but in our bank account, we'll have $43,485. That's pretty good. Then, okay, so if I started working at 20 years old, I'm now 40 years old. Then another 60 would be 300 months. Delete here. 300 months, that would be 25, doing this for 25 years. And we have 37,500 saved. We have almost 60,000 in the bank. And then another 60 months with 36. So this would be 30 years. So if you're at 50 years old now, you have $45,000 in the bank. But just to be clear, now you have 150. Ooh, that's too much. Sorry. I need this. That's too big. You're not gonna live that long. Sorry. I wish you could. So you have $45,000 that you've saved, and you have almost 80,000 in the bank. And so what did I say that this was? So 5, 10, 15, 20, 25, 30. That puts you at 50 years old. And since I'm running out of time, let's jump right up to 65. If you did it till you're 65. So here would be 25, 30 years old, 35 years, 40 years old, 45 years, 50 years old. And so I need another 120 to add on that, so 480. So you did it for 480 months. That would be, wait, yeah, 5, 25, 30, 35, 40, 45, 50. You got to go to 65 at least. So I need 180 onto that. So that would be another 60. So 540 months, 65 years. So after 65 years, you will have saved 65,000, yeah, $65,500. But in the bank, you will actually almost have triple that. You'll have $164,178. That's a lot of money, only saving $100 a month. And as you get older, you'll probably start making more money. You should up how much money that you're plotting in. So if you're plugging in more than $125 a month, this total will actually get bigger even faster. All right, well, that was a lot. I am done. So our Star Wars fun fact of the day: the sound of the hovering battle tanks from Episode 1 in The Phantom Menace was achieved by running an electric razor around a salad bowl and then digitally lowering the pitch. And here's a picture of the object that I'm talking about. Well, that's all I got for today, folks. You have a great day. Goodbye.